We've been working for a little while on CVA6 CHERI. So CVA6 is an open source core in System Verilog. That was its first virtue and what caused it to be picked up by people who wanted to work with System Verilog and not Chisel a long time ago. And actually it's gotten a few users picking things up and extending it, and there's actually quite a lot of activity going on with the CVA6 project. I had a slide here in an earlier version where people are working on adding vector extensions. There's floating point, there's hypervisor been added, and very active project because different users want different things, and it's really nice to see them cooperating together in the open source community to add features to the core. So we thought, if we'd been working on some research implementations, but we thought this is the group around Cambridge University, and now with Capabilities Limited doing some commercial work, we thought if we're going to be making something that people can actually use in the world, then let's pick up a core they're already using and add CHERI to it, and then we'll understand how it affects a core that people are really using, and also will be something useful. So when we stepped into this project, 0 Day Labs had already done an initial work on this. They're down in Portugal. And so we picked up their work, did lots of extensions, a big extension to their work, moved it to the version of the ISA that's being ratified, and also did verification on the fundamental capability operation. So we're building on that together and working together with them a little bit. We've taken the baton from them now. Bruno, who's working on that, is finishing his PhD, and so we're mostly working on that code base now, Capabilities Limited. Okay, so these are bits of what I want to talk about today. We've implemented the RV64Y candidate extension, which included a mode switch instruction, which has a little bit of interesting microarchitecture. We've done quite a bit of verification. We've done some amount of area optimization. We want to do more, but that's been fun, and some timing optimization. Obviously, we had to do quite a bit in the decode of the new instructions, but structurally, already the execute unit was calling some special functions that are analogous to functions that we had in a shared library called CheriCaplib. So if you're doing an implementation of CHERI, you should check out our CheriCaplib implementation. Originally, all of the functions were in BlueSpec, which was a hardware description language we were using for research. But Bruno did versions of those functions in System Verilog, and we pulled those in, done formal verification, tidied things up a little bit, and made a fork of that implements the format from RV64Y. And so once we updated the decoder, mostly the capability logic unit was just calling those functions, and when we updated the library and swapped it in, the new functions worked as they were intended, so that really helped clean up things. Then one of our favorite challenges here was the mode switch instruction. So RV64Y, in order to save encoding space, allows you to switch between pure capability mode, where you interpret every pointer as a capability, where you check the bounds against the upper half of the register, to non-capability mode, or integer mode, or legacy mode, whatever you want to call it. And in that one, you take the lower bits of the capability and you check that they're within the bounds of your default data capability. And this is how you would run software that doesn't know about CHERI capabilities. Well, sometimes you want to intermix those operations. So say you have an operating system kernel that is handling user space pointers as capabilities, but all of its own pointers are just integers checked against a default data capability, which is one thing you could do. Well, you might want to switch quickly between using one ISA and the other. Well, what Morello in the previous RV60 CHERI RISC-V architecture did is they had a whole new set of loads and stores with that access the alternate base. But if you want to save your encoding space, maybe we can just have a small instruction that just switches the mode and then switches back again. But for that to work efficiently, we want to be able to switch the mode in the decoder on the fly. And so this was a little bit of a challenge. So PCC has the program counter capability has a few fields, but one of them is the mode bit. And we allow the decoder to own that mode bit. So if you ever want to know what's the mode, the decoder tells you that bit of PCC. So you have to assemble things a little bit to find out what your PCC is. And what that does is, as you're decoding instructions on the fly, potentially superscalar, because this one can do dual issue, as you're decoding instructions on the fly, if you find one of these mode switch instructions, which is entirely defined in the instruction itself, it's not reading from a register, you can authoritatively switch the mode, and the next instruction you decode in the next mode, then it gets switched back again, you authoritatively decode again in the new mode, and that way you can get full throughput while swapping between modes. So that could be important for your hybrid software. So that was a fun challenge and produced lots of counterexamples for us to fix. Okay, this is what I just said there. Okay, so verification. This was the library I told you about. We actually set up a formal verification framework for asserting equivalence between these two using open source tooling that can do formal verification. It's not as powerful as Jasper Gold, but Symbiosis, which we're using, is plenty capable of doing combinational functions and proving that they're equivalent and giving us counterexamples. So this is just to encourage you, if you want to do a system Verilog implementation, even if it's super secret, come poke around in our library, because you can probably find useful, fairly high performance functions. And then if you're very kind, you can commit improvements back, or you could have forks or extra versions that are pipelined and things like that are also proven correct. And maybe there will be some interesting projects based on that too. So these are some of the properties that we are proving equivalence of. Area optimization. Okay, so this is really fun. When we first started on the version that Bruno had done, we found lots of copies of the program counter capability sprinkled in the BTB and in the early instruction fetch part of the pipeline. Even the scoreboard, which has a record for every instruction, had many copies of the program counter capability. Now, we knew from experience that the bounds on your program counter capability are the same usually for an entire compile unit, or at least a large amount of your software, since you're, at least the way we generate code usually, you reach your globals relative to your program counter capability. So there's within a function, probably between several functions, your bounds don't change. So we thought we should be able to gain a lot of efficiency by moving all of the bounds of the capability just to this issue stage. Sorry, the bounds of the program counter capability. So we allowed this issue stage to hold one copy of the bounds of the program counter capability, and the rest of the entire pipeline just has 64-bit addresses for capabilities. And that allowed the front end of the pipeline, for example, to revert to exactly upstream without any capability changes, which was really satisfying. And we perform our bounds check and forwarding from the issue unit. Now, you might ask, what happens when somebody does do a jump that changes the bounds of the capability? Well, we're able to detect that in execute, and because execute reads the next target that they're going to jump to, and that can notify issue stage, and it can stop on a dime and wait for the last two stages of the pipeline to flush before updating the, or not flush, but to write back before updating the bounds of PCC and continuing. So that way we get to keep one copy of bounds in the whole pipeline. And we're evaluating the performance of that, but that was so far it seems to be a good use of area. Okay, on execute functions, we did a little bit of optimization here. One thing is we had a special function for setting the address. We also had another function for incrementing the offset, both with a representability check, which is somewhat expensive floating point type thing. And what we decided to try, and passes timing fine, was to just move the set address function to be a shared resource at the end of the ALU pipeline, and just perform a normal add or not, and feed that into the set address function. So we only have one representability check in the ALU. And that allowed us to save a little overhead and hasn't caused any timing issue. So this was the current state of our overhead. We have a lot of overhead in the issue stage, so we'll keep working on that. And let's see. Oh, here was one more timing optimization. So the last timing optimization to fully pass timing was making the capd code parallel to byte select. And we run lots of software.